In space, no one can hear you scream. You've heard that. It's true. And almost everyone leaves it there, as a curiosity, a fun fact, a tagline for a horror film. But if you actually follow the logic, it leads somewhere extraordinary. If sound can't travel through space, if that specific type of wave is forbidden, then what can travel through space? What is space actually carrying right now as we speak? The answer isn't just light. It's deeper than that. It involves waves that need no medium whatsoever, waves that travel through the structure of space itself, and waves so difficult to detect that we spent a century building instruments sensitive enough to find them. Space is not silent. It's full of information, traveling in registers our bodies were never built to receive. I'm Paul Dirac. Let's trace this out carefully. Sound is a mechanical wave. That word, mechanical, is the critical one. Sound propagates by disturbing matter. A vibrating speaker cone pushes the air molecules in front of it. Those molecules push the ones next to them. A wave of pressure, alternating compressions and rarefactions, moves outward. In water, the same thing, mechanical disturbance of the medium. In steel, faster still, because steel is denser and more elastic. The speed of sound is entirely determined by the properties of the medium carrying it. Vacuum has no medium, no molecules to compress, no matter to disturb. The vibration has nothing to propagate through. Sound doesn't slow down in vacuum. It stops existing as a propagating phenomenon. Between stars, the interstellar medium contains roughly 1 atom per cubic centimetre, extraordinarily thin by any earthly standard. For sound, that's effectively nothing. The mechanism simply doesn't work. But for most of the 19th century, physicists were convinced that something similar must be true of light. Light waves, they assumed, must require a medium, the way sound requires air. They called it the luminiferous ether, a substance invisible and undetectable, filling all of space, through which light oscillated as it travelled. It seemed logically necessary. If light is a wave, it must be a wave of something. In 1887, Albert Michelson and Edward Morley designed an experiment to detect the ether directly. As Earth moves through space, they reasoned, it should move through the ether, and light travelling in the direction of Earth's motion should take slightly different time to complete a round trip than light travelling perpendicular to it. They built an interferometer of extraordinary precision to measure this difference. They found nothing, no difference, zero. The ether showed no trace of its existence. For nearly 20 years, this result sat uncomfortably in physics. Then Einstein's special relativity explained it completely. Light is not a mechanical wave. It's an electromagnetic wave, oscillating electric and magnetic fields, each generating the other in a self-sustaining cascade. Maxwell's equations describe this perfectly. A changing electric field generates a magnetic field. The changing magnetic field generates an electric field, and the whole structure propagates through space at a fixed speed, 299,792,458 meters per second, requiring no medium at all. Light doesn't travel through space the way sound travels through air. Light is a disturbance in the electromagnetic field, and that field exists everywhere, permeating all of space. The field is the medium, and the field needs nothing to sustain it except the laws of electromagnetism. This changes everything about what the silence of space means. Space isn't carrying sound, but it's absolutely carrying electromagnetic radiation, and not just visible light. That's the part worth expanding. Visible light, the narrow band of frequencies your eyes evolved to detect, is a tiny slice of a continuous electromagnetic spectrum. Radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, all the same phenomenon, oscillating electromagnetic fields propagating at the speed of light, differing only in frequency and wavelength. All of them travel through vacuum without any medium. All of them fill space right now. The universe is not electromagnetically quiet, it's extraordinarily loud. The cosmic microwave background, the afterglow of the Big Bang itself, washes over Earth continuously as microwaves, a nearly uniform glow from every direction in the sky, the oldest light we can detect, emitted 380,000 years after the Big Bang, when the universe first became transparent. Pulsars, rapidly rotating neutron stars, sweep beams of radio waves across thousands of light years with clockwork precision, so regular they were initially mistaken for signals from an extraterrestrial intelligence. Gamma-ray bursts, the most energetic events known in the universe, release more electromagnetic energy in a few seconds than the Sun will emit across its entire 10 billion year lifetime. Space is drenched in electromagnetic information at every frequency. We receive almost none of it with our unaided senses. Our eyes respond to a tiny window. Our ears respond to pressure, not fields. What we call the silence and darkness of space is almost entirely our biological limitation. But now, and here's where the story gets genuinely strange, electromagnetic waves are not the only thing space carries. There's something more fundamental, something that doesn't just travel through space, but travels as a disturbance of space itself. Einstein's general relativity, published in 1916, described gravity not as a force between masses, but as the curvature of space-time caused by mass and energy. Masses follow curved paths through curved space-time, what we observe as gravitational attraction. But the theory predicted something more. Accelerating masses should generate ripples in space-time curvature, propagating outward at the speed of light. Not waves in space, waves of space. As a gravitational wave passes, the actual distances between points in space oscillate. One direction stretches while the perpendicular direction compresses, then they swap back and forth at the wave's frequency. For nearly a century, this prediction sat unconfirmed. Gravitational waves interact so weakly with matter, passing through it almost entirely unimpeded, that detecting them seemed almost impossible. The engineering challenge was staggering. The predicted distortions were so small that building a detector sensitive enough seemed beyond reach. Then LIGO was built, the Laser Interferometer Gravitational Wave Observatory. 2 facilities, one in Louisiana, one in Washington State, each consisting of 2 arms, 4 kilometers long, oriented at right angles. A laser beam is split, sent down both arms simultaneously, reflected back by mirrors, and recombined. When both arms are exactly equal length, the beams interfere destructively. The detector is dark. When a gravitational wave passes and stretches one arm while compressing the other, the interference pattern changes. The detector registers the wave. The sensitivity required is almost incomprehensible. LIGO can detect a length change of 1,000th the diameter of a proton across 4 kilometers of baseline. The mirrors are among the most geometrically perfect objects humans have ever manufactured. The laser is stabilized against every known source of noise. Seismic vibrations from traffic, from ocean waves, from human footsteps kilometers away are cancelled by multi-stage active isolation systems. The quantum nature of light itself, the fact that photons arrive randomly, creating shot noise, is the fundamental detection limit, and advanced LIGO uses squeezed light states to push even below the standard quantum limit. On September 14, 2015, at 5:51 a.m. Eastern Time, both LIGO detectors registered a signal lasting 0.2 seconds. The signal matched perfectly the predicted waveform of two black holes, each roughly 30 solar masses, spiraling together and merging, 1.3 billion light-years from Earth. The gravitational wave had been traveling through space for 1.3 billion years, passing through everything in its path, essentially unimpeded, and arrived at Earth as a distortion of space-time 1,000th the diameter of a proton. LIGO measured it. This was not just a detection. It was the opening of an entirely new sensory channel for observing the universe, one that sees things invisible to any electromagnetic telescope, because black hole mergers produce almost no light. Gravitational astronomy began on that day. Since then, LIGO and its partner observatory Virgo have detected dozens of events, black hole mergers, neutron star mergers, and signals whose sources are still being analyzed. Now let's take stock. What does space actually carry? Electromagnetic waves, photons, self-sustaining oscillations of coupled electric and magnetic fields traveling at sea, carrying information about every hot, charged, or energetic process in the universe. Gravitational waves, ripples in space-time curvature itself, also traveling at sea, carrying information about the most massive and violent events, merging black holes, neutron star collisions, possibly the Big Bang itself. Neutrinos, nearly massless particles produced in nuclear reactions, including in the Sun's core, interacting so weakly with matter that they pass through the entire Earth as though it weren't there. Right now, about 65 billion solar neutrinos pass through every square centimeter of your body every second. You don't notice, they don't stop. Cosmic rays, high-energy protons and heavier nuclei, accelerated to extraordinary energies by supernovae and other violent events, traveling through space at significant fractions of the speed of light, constantly raining down on Earth's upper atmosphere. Space is a medium of extraordinary continuous activity. The silence we associate with it is not space's silence, it's ours. Our ears evolved to detect pressure waves in air. Our eyes evolved to detect electromagnetic radiation in a narrow frequency band. The vast majority of what space carries, most of the electromagnetic spectrum, all of the gravitational waves, all of the neutrino flux, is completely invisible to us without instruments. What we've built instruments to detect is almost certainly not everything that's there. Here's the thing that I find most worth reflecting on. Sound cannot travel through space because sound requires bulk matter, molecules, atoms, a physical medium to carry the mechanical disturbance. Space between stars has almost none. But notice what that tells you precisely about what space is. Space is not nothing. It contains the electromagnetic field. It contains the gravitational field, which is, in general relativity, the geometry of spacetime itself. It contains the Higgs field, responsible for giving particles mass. It contains quantum fields for every known particle type in their ground states, seething with vacuum fluctuations that produce measurable physical effects. The vacuum of quantum field theory is the lowest energy state of an extraordinarily rich physical structure. What we call empty space is full, just not of the specific thing that sound requires. Sound needs matter. Space has fields. The silence of space, understood properly, is a statement about the absence of bulk matter, not about the absence of physics. And then this: for all of human history until the late 19th century, we understood the universe through visible light alone. Then radio astronomy opened. Then microwave, infrared, X-ray, gamma ray. Each new window revealing classes of objects and events invisible to all the others. In 2015, the gravitational wave window opened and immediately revealed black hole mergers we had never directly detected before. Each new channel carries different information about different physics. We've opened perhaps a handful of the channels space offers. There is almost certainly physics being communicated across space right now in modes we don't yet know how to receive. The universe is not quiet, it is speaking continuously in every direction in electromagnetic waves and gravitational waves and neutrino fluxes and cosmic rays and modes we haven't discovered yet. The silence of space was never space's silence. It was the silence of an organism with ears tuned to one narrow range, standing in a concert hall of extraordinary richness, hearing almost nothing. What we've learned to hear so far, that's not the complete picture. It's the beginning of one.